is a research scientist at DeepMind working on the open-ended NC. He has done some great work in unsupervised environment design, which seeks to automate the creation of challenging tasks.
Very good. Yeah.
Okay. Michael has done some great work in unsupervised environment design, which seeks to automate the creation of challenging tasks as agents efficiently and generalized without ever seeing human design environments. So going in the completely opposite direction from Chelsea, which was all about real robot reinforcement learning, Michael's talk is on this topic. RL's future is in virtual environment. So I'll hand it over.
Set up the AV real quick. Okay. Everyone hear me? Cool. Okay. Yeah. So hi, everyone. Today I'm going to talk about how I think RL's future is in virtual environments. And so first, what do I mean by this? Well, what I mean is that most RL experience in the future is going to be within programmatic environments, completely separate from, sorry, just can't see my, there we go. Or, okay, hopefully it's good. Cool. What I mean is most RL experience is going to be within programmatic environments, completely separate from reality or from humans. And so why I think this is important is because virtual environments will have faster algorithms than we can run on real environments. So virtual environments are sort of like video games or like the holodeck. You can save or reload. You can reset your state to arbitrary situations. You can design a natural progression of environments in order for you to learn skills in a reasonable order. And you can set up practice environments where you design it so that you can hone in on a specific skill. And all of these, in their own way, mitigate the exploration problem. And so what this says is that that Sutton's bitter lesson. Sorry, I can't quite see my. Okay, let me just sort this out for a second. Okay, sorry about that. So what this implies is that by Sutton's bitter lesson, the best methods are going to specialize to virtual environments because it's much easier to, because we have all these ways of getting around the exploration problem, we're going to be able to find algorithms that work substantially faster than any algorithm could in the real world. And so because of this, we're going to scale the best with compute, are going to take advantage of the fact that we're in virtual environments. And so another reason why I think that we're going to, in the future, we're going to be spending most of our time in virtual environments is because today's most impactful environments are already all virtual. So we have environments for math and code, which can be clearly verified just all on a computer running in a data center. We have things like tool use or computer use, which can be run just by simulating an OS or whatever tool that you're trying to use. And we have things like thinking models, which run just by running more and more computation on their own outputs. All of these things are things that you can run completely in a data center without leaving the data center and going to trying to find things in the real world. And so there's a lot of complex behaviors you can learn in data centers, and there are a lot of economic value that you can get just by making models that are very good in these sorts of environments. But I think it's even stronger than this. I think that virtual environments have a strong economic advantage. This is because when you're running on virtual environments in a data center, you can do 1 million operations in the same time that it would take you to go all the way to the real world, run some experience, and then try to bring that back to the data center and do your policy update. And so this is such a big advantage that even if the task that we care about is in the real world, we would much rather take the real world, move that into some sort of simulated world in the data center, and then spend all of our time iterating on this, rather than continuously take the expensive back and forth trip to go continuously touch reality. And if this sounds difficult to you, just imagine doing this for chess. So in chess, you could go watch a few chess games and really understand the rules of chess. And then you can go come up with a simulator and run as many games as you want, playing against yourself in chess until you become superhuman and really like understand the game of chess better than any human does on Earth. And the reason this is possible is because chess is a situation in which there's not very much empirical uncertainty. It's very easy to understand the rules of chess, but there's a lot of logical uncertainty that once you understand the rules of chess, it doesn't that in order to get your policy, you still have a lot of uncertainty about what the best move is. And so you don't really understand the consequences of your own belief. There's a lot of work that you can do just by churning compute in a data center, finding a better policy. And so one natural question to ask is, when we look at the real world problems that we care about, how much of the uncertainty that we have is empirical uncertainty about reality, about the nature of how things are, and how much is it logical uncertainty, that we know how things are, but we don't know what to do about it. And so what I want to claim is that empirical uncertainty is nearly limited by existing offline data. That is, once we take all of the data that we have on the internet, that most of the rest of what we would want an intelligent agent to do is logical uncertainty. And so once we can find a way to take all that offline data and bring it into a simulated environment into the data center, we'll have a lot of RL that we need to run, but it will be run in this sort of virtual environment without coming back to physics. And so to try to dive into this hypothesis a bit more, imagine the paths to real world general policies. And so the ways of trying to get environments to train agents in to do this would be either to manually reuse existing simulators or games, manually design simulated environments, or collect data from robots and humans. And all of these scale with human labor, right? They're expensive and time-consuming to do. And the bigger lesson tells us that methods that scale with data and compute will ultimately outperform those which need to scale in terms of human labor. Meanwhile, we see the generative AI revolution pushing forward the advancements in text, images, audio, and video generation at an astonishing pace. So much so that every time I give this presentation, I find that it's more and more out of date because just in the past month, there's new models that come out that obsolete everything that I've previously put on the slides. And so this leads to the natural question. What if we could generate entire interactive environments using all of the videos on the internet? So effectively, what I want to do is build the holodeck, right? Can we take all of the things that we know about reality on the internet and put those into a simulator where you can just ask for the situation that you want and be able to run all of your rollouts in this sort of simulated environment, reducing the question of making a good policy to simply one of logical uncertainty. And so this was the motivation for the Genie project. We're trying to make generative interactive environments with this great team of my collaborators at DeepMind. And Genie's mission was to learn generative interactive environments from only videos that is both playable by humans and by AI agents. And so Genie is like an action controllable video model and a foundation world model. So it's similar to a video model in that it uses these sorts of generative AI technologies like diffusion or masking. But it's different from a world model in that it's not world models, video models tend not to be action controllable. It's like a world model in that it tries to like do this sort of action condition generation and learns it completely from data. But world models tend to need action labels. And if we want to really train on all of the videos available on the internet, you would have to do this in a way that doesn't require action labels because most videos don't have them. And so what we did was, so the Genie model is basically trains on video data only, infers actions to use to try to most effectively compress the future into a set of small latent actions. And then at inference time, the user can start from an initial frame and given those latent actions, try to construct rollouts, or it will try to construct rollouts so that the human is effectively playing a game generated from that initial frame. And so a lot of the trick here is in this latent action model, where we take pixel inputs, which lead and funnel them through this like latent bottleneck. where the latent encoder tries to encode the information from the past and seeing one frame into the future into a small bottleneck such that it can predict, such that the decoder can effectively predict the next frame. And so in addition to the latent action model, we use a video tokenizer, which encodes all of the frames from the trajectories and encodes them into a set of video tokens. And then we have a typical dynamics model, which is just a generative model of this typical sort that you see in generative video modeling to predict the next frames from the past video tokens and actions in an autoregressive way so that it only sees the past. And what we find is that this recipe is fairly scalable, that we can do the natural sort of scale and law analysis. And as we add more scale, as we make the network bigger and we spend more computation on it, we find that it gets better and better at becoming a generative video model or generative environment model. And so this is what we did. We trained on a data set of internet videos of platform gameplay. And we can find that when we plug in a picture and play the actions ourselves, we can generate a wide variety of environments that show a bunch of complex, different sorts of experiences that an agent in these environments could sort of play. And so these results were last January. And since then, okay, let me go through a few other features of this first. So I guess from the same starting frame, you can see a bunch of different sorts of experiences that you could generate. So it's clear that it's not like, it's actually sort of an environment that you can walk around. You can do a bunch of different things from the same state. Moreover, we can prompt it with out of distribution images, and it does some reasonable behaviors, even things that are quite different from the sort of platforming gameplay that's seen before. And moreover, if we feed in the same sequence of latent actions for a bunch of different starting frames, they behave in very similar ways, implying that the latent action model is coming up with some sort of semantically meaningful decomposition of what each of these actions means that would be repeatable across different states. Moreover, we see some emergent behaviors already, like when you wiggle the screen around with 0875, which is up, right, down, left, you can see that that the foreground moves a lot faster than the background, implying some sort of parallax, which sort of gives the illusion of an extra dimension. And none of this was specialized to the platformer data set. We can run all the same things on a robotics data set, and we get. And so all of this is to say that that even in this case that we want to do like train agents to be able to do a bunch of real world behavior, because of the amount of data that there is available already on the internet, and because of the power of our generative modeling techniques, we can take this problem that is in the real world and essentially make it into a virtual world. And this allows us to not only think of the virtual environments of like math, code, thinking, but also any sort of environment that we want to work in the real world. We could imagine being able to use the same sorts of advantages that virtual environments have, such as saving, loading, resetting, designing them, or making these sorts of practice environments. And so what I want to talk about next is, okay, if we believe that these sorts of environments are going to be the future, if we believe that the vast majority of the things that we are going to be doing in the future are going to be in these sorts of virtual environments, how can we make algorithms which actually take advantage of those features? And how can we use all the tools that we have already to make something that's even more efficient with these features? And so this brings me to a project that I did in grad school with Natasha Jakes, Eugene Vininsky, and a bunch of other fun collaborators at Berkeley, in which we basically worked on this problem of unsupervised environment design. So supposing this context where you could design training environments for agents. So in this case, you have a grid world where you have a set of blocks that you can place, a starting location and an ending location. And you have the set of the set of parameters that you can use to specify the environment. So you can, in this case, it's like all of the blocks in the starting and ending location. And given that specification, you can make it into a POP. So you can try to, you can then design the environment that you want the agent to train in. And what this does is it gives us an opportunity for a multi-agent autocurricula where you can choose the order of environments, starting from very easy environments to solve and moving to more complex environments over time. And so we're not the first to do this. This was done in a project at Xland and adaptive agents, DeepMind. It was done in procedural content generation by reinforcement learning by Julia Tugalis' lab, and paired open-ended trailblazer by Jeff Clune. All of them have shown these, along with us, have shown that finding the right curriculum of training environments can lead to not just faster convergence, but more complex behaviors. But should be familiar to everybody in the field from results like AlphaStar or AlphaGo, where the changing of opponents in those environments was critical in terms of creating the automatic curriculum, starting from learning simple behaviors to, over time, learning complex and superhuman behaviors. We're basically trying to harness the same sort of multi-agent autocurricula, but in the context of learning environments. And so this opens up some weird sort of philosophical questions. So typically in RL, we're trying to maximize expected return on, and any sort of uncertainty that we have, we just sort of average over it. And this is typically all right because the probability is unknown. If we are trying to win at poker, we know that the distribution of cards in the deck is going to be sampled from a uniform distribution. And so we can sort of just take the expected value and sort of the reasonable thing to do. But in this context, we don't know which environments we're going to be deployed into. There's not really a distribution of environments that is the right one to sample from. And so we move from this context that's typically decisions under risk, which is situations where the probabilities are known, to this context of decisions under ignorance, where the probabilities are unknown. That you just have a set of possible things that you could be trying to deploy into, and you want a policy that's going to do reasonable things regardless of what reality actually is. And so historically, this sort of represents a split in decision theory between sort of the von Neumann line of decision theory and the John Milner line of decision theory. If you always happy to discuss this offline, I can really nerd out about this for hours. But basically, we have this theorem in this paper that every reasonable strategy for decisions under ignorance can be represented by some adaptive training distribution over environments. And so really anything that you might want to set as your goal here, you can implement somehow through some sort of adaptive complex training distribution of environments. And so quickly, I want to go over 3 sort of reasonable strategies that you might expect to work here. One would be domain randomization. This is just okay, we don't know the distribution, but let's just treat it as random environments, just uniformly from their space, and try to maximize the expected value anyway. The second would be adversarial training. We try to think about all the environments we could be deployed in and try to maximize the worst case performance in any of them. And finally, we have minimax regret. This is trying to look across all the possible environments and find a policy which has the best worst case regret. Put a different way, it's a policy which has the smallest distance from optimality in any environment. So if we look at this matrix on the right, where the columns are environments and the rows are policies. This bottom policy, pi3, is nearly optimal in every environment. It is suboptimal. It is less than policy 1 by 3 points in environments 2 and 3. Because any of the other environments have some, or any of the other policies have some environment in which they completely fail. And so the min-max regret policy effectively tries to find a policy which succeeds whenever there's a policy that usually succeeds. And so to put this into more visual evocative terms, domain randomization is sort of like training on random environments. Adversarial training is sort of like training on environments that are trying to minimize your utility. So this is environments in the maze context would be environments that are unsolvable. These environments get 0 utility for everybody, and so they're the actual adversarial ones. And minimax regret would be trying to train on environments which have the smallest distance between, or in which the agent is the most suboptimal. So if you have an agent that can actually navigate around reasonably well, then a minimax regret environment is going to be one in which the agent, like in its wandering, finds the goal at the last possible place that it looked for it. And so it's going to be these sorts of maze-like environments where there are a lot of back alleys where you can go the wrong way and you have to come back and find the actual minimax or actual goal. And so a quick sketch of how you could try to optimize for this. You could, it's like, so the typical adversarial training way of doing things would be an adversary designs the environment to try to reduce the utility of the protagonist. A small modification of this would be to add another player and to motivate them so that the adversary is trying to maximize the difference between the two players to maximize the regret. And the protagonist and antagonist are each trying to perform well in their own environment. And so we call this algorithm paired for protagonist antagonist induced regret environment design. And you can show that if the adversary and antagonist are a team and you find the zero-sum like Nash equilibrium between those two teams, that this will give you the minimax regret solution for the protagonist. And so when we run this, we find that the paired algorithm works better than domain randomization or the worst case algorithm, especially in these environments that are like much more like feeling like designed by humans. But since then, the field has sort of like adapted to a few new ways of doing things. And so to quickly go through some other things we've tried, we found that you can get a lot of work on this front, actually just out of curating environments and replaying them in an important way. So this in this setting, we basically sample environments from the distribution and use the trajectories from them to compute some sort of score for how, like some sort of proxy for how much regret you would get in this environment. And then you use that score to update a buffer to keep track of which environments have given you high regret in the past. And then you, rather than just always sampling from the random distribution, you replay samples from this buffer to sample the ones that have higher regret. And then you like randomize how often you do this to some degree so that you always can keep getting new levels. We found that this is a pretty good way of training environments, but an even better way is to not even train on the environments in which you just randomly sample, because we found that introduces a bias. And it's actually better to train on the less data to improve performance. And you can go one step beyond this and actually take those environments that you keep in the buffer, and rather than just randomly sampling new environments and curating them, you can try to evolve them over time. So take the edits that were high regret and try to edit them to continue to make them high regret. And so what we found is that this creates a interesting and useful distribution of environments that starts from very simple things and moves to very complex things with results in policies which generalize far out of the distribution of actual training environments to mazes that are like much bigger than anything that we've seen in training. And we find that when we compare the performance of paired PLR and Excel, that we find that PLR beats paired and Excel tends to beat PLR. And one thing that I wanted to note for anybody who's sort of considering getting into the space is that this sort of research is now much easier than it was when I was in grad school. So when I was in grad school, we would need to run this on like some sort of small cluster where you would need to run a bunch of simulations and spend a lot of time running a bunch of different sorts of environments. Since then, there's been really fast implementations of these environments on using like pure JAX-RL. And these have, of course, been extended to Marl. And since then, there's been re-implementations of all of these sorts of algorithms that I've been describing before in JAX on these sorts of fast environments. And now if you have one GPU and want to experiment with like new modifications to these algorithms, you can do it in less than a day, just given one GPU. And so the iteration speed is really actually something that is in reach for like small academic projects. And I think that I really want to emphasize that this space is very new, that not very many people have tried to do very powerful things. And yet a lot of the things that I've seen tried really move the baseline significantly. And so I think this is a really useful way to contribute meaningfully to the field. But one thing that I wanted to point out is that that if we're moving into these virtual environments, that typically like one useful feature of training on real environments is that the complexity of the environment sort of comes with the environment. Like if you look around the real world, there's a lot of complexity, so much more than you can make in any sort of video game, regardless of how many devs you throw at it. But when you're working in virtual environments, that complexity, you somehow has to either build itself or be specified. And one thing that we know sort of from evolutionary biology is that the environments, the complexity of the environment is reflected in the complexity of the organism. So the hummingbird only needs to hover in that sort of way so that it can get nectar out of sort of flowers that otherwise it wouldn't be able to use. And the hermit crab has that sort of like hermity behavior because there are things that it can nest within. And so if we want to see these sorts of complex behaviors, we're going to need to find ways of having this sort of complexity emerge out of otherwise simply specified environments. And so in order to try to get some sort of handle on this challenge, me and Ed Hughes and some other people working on the Open team and friends sat down together to try to come up with our understanding of how this sort of open-ended complexity, what the goal is of trying to come up with this sort of open-ended complexity, and also like what a good like starting point for people trying to get into the space of trying to understand how to make these sorts of systems work. And so the high level of this paper was that we were trying to find a formal definition of open-endedness that is workable, to illustrate that this can be used on the path towards ASI, and argue about some of the safety challenges that are sort of at the core of open-endedness research. And so as a high-level rough definition, open-ended systems are those which endlessly produce new and interesting things. So this is inspired by evolution, where the open-ended complexity of new and novel things is sort of like one of the defining features of it. That like all of the things that we sort of see around us have been built out of a bunch of very small changes over a very long course of time. And so just to fast forward to a rough definition, one way that we thought that it was useful to define open-endedness was as this idea that a system is open-ended only if it is both novel and learnable. So it's novel if it's continuously more surprising over time. And it's learnable if, given more observations from the system, you can learn how to predict the system better. And so these two things are somewhat obviously in tension. To see how it navigates sort of the interesting example of the noisy TV, this sort of system would be novel because it would keep surprising, but it's not learnable because there's not really structure to it. But it would, you could get an open-ended system that is a TV that keeps switching to different channels and has more interesting content over time. Because as you learn more from each of the shows, you can better predict what's going to be on other shows, and you can actually learn to predict the system better. And so this definition of open-endedness is definitely observer dependent. Things that are open-ended for humans might not be open-ended for an alien system who already understands how all of these things work. And so maybe things aren't novel anymore. And so this definition sort of captures a lot of classic examples of open-ended systems in AI, things like AlphaGo, AlphaGo, the Adaptivations Project, or Poet, which we mentioned earlier, that these were open-ended, but in sort of very narrow domains. And it also sort of cuts out some of the most impressive systems that we see now that are very general, but we wouldn't say open-ended. Basically, things like next token prediction, where you have some sort of fixed knowledge that it could look like these systems are dramatically improving over time, but to some extent, they can only sort of match the things that are in their data set. And so while they are learnable, they're no longer novel. Like eventually, once you've minimized your loss on the whole training data set dozens of times over, that seeing it again isn't going to be novel anymore. And so there are several ways in which the field has moved more towards open-ended foundation models. If you want to see more of these discussed in detail, I would really recommend checking out the paper. And moreover, anybody who's sort of interested in the field or knows people who are interested in thinking about open-endedness, I think it's a really good resource to just use to sort of get into the space. And we're always happy to chat about it, so just drop us an email at any time. And with that, I think I'm slightly over time, so I want to just thank the audience. Yeah.
So I have several questions. So the Genie 3 just launched like today. I saw it. It's pretty interactive. So I want to know what kinds of efforts DeepMind have you made to make this interaction like without latency. So another question is like for world modeling, like you will probably have some kinds of way to verify and measure how good your world model is. Probably through like a reconstruction loss or something like that. But in the setting in RL, like you're using that world model as a simulator to generate more data for the later upcoming decision making. So how do you ensure like your world model, like to what extent you want your world model to how good it is, so that the hallucination in the visual thing won't have a bad impact on your follow-up dynamics learning. And also similar to this question, like how do you design your like as on Genie 3 there is an agent trained on it. So how do you make sure your agent is not really learning the shallow visual representation than the capturing the real data?
Thanks for the questions. I will probably have to take parts of that offline, but always happy to chat. I'll be around all week. But I guess for the first part, I guess you were asking about how close these are to like real time, I guess. So Genie 2 was built in a way that could be made into real time. And I think Genie 3, just checking what I can actually say about things. Yeah, so Genie 3 was real time. And I imagine that these things are going to be getting quicker as things progress, in the same way that sort of video models that you can see sort of in the open have been getting quicker. This technology is very new, and there's a lot of things that you can do to make this a lot more like a lot lower latency. In terms of like, yeah, like the exact like forgetting all of the parts of your question. I guess in terms of how you would generally evaluate these sorts of things, I think that you can evaluate them similar to how you evaluate, at least on the video model front, some video models. I think that like part of the ethos of Genie 1 and Genie 2 was that in trying to make these things something that humans could use, you really up the quality standards a lot. And so like they're gonna hopefully be a lot better than existing world model implementations, where you're trying to make it good enough that an agent like it's sort of like dog fooding. Like if you as a researcher is the one who's going to be going and playing this thing, then you're much more likely to notice if it's not good in terms of like making a bunch of rollouts than you are with like some sort of internal world model. Yeah, and I guess in terms of like the how the agent was trained, I actually am not privy on all the details of how like this like that sort of thing worked in Genie 3. So I'm not sure if I can say too much about it in an informed way. Yeah.
Thank you. Okay, so I was wondering about the extent to which versions of doing video generation models, including Genie, might run into some challenges. So maybe my real question is like, are there some things in the universe that are very computationally expensive to simulate, and that will eventually make it difficult to like include those in really any type of simulation? And it's like, because right now you're training this over some like autoregressive model, so it's got some limited amount of compute based on that, as you know, run into some issues at some point.
Well, I mean, I could definitely make adversarial things, which this would probably be pretty bad with. Like, if I made it like, if I made it a like, I don't know. I guess like you could make programs that are very difficult to predict and like show their outputs on a screen. Like, it probably, even knowing what the program is, it's going to have a hard time doing that. Yeah. Um, I can't think of any good ones. You might worry about like water or something, but it seems like those are done well in video games. It would have to be something that's not really done well in video games. Right. So I think on those things, I think it would be give you like valid looking but wrong guesses because I think humans are very unpredictable. And so I think, yeah, so I think it would give you things that are like quite plausible, and just aren't the things that you end up saying. Does that make sense?
Um, so I'm curious from like the environment design perspective, as we look to scale to more complex environments. I think like an obvious application is Genie, so we can search those environments to try and benchmark station. Do you think from that perspective, Genie, which is like a sort of, I guess like a neural world model, is the most effective compared to say on the Epic, where your environment searches over a code space?
Yeah, so just to repeat the question, the question was about whether Genie is the most effective way of doing the sorts of environment searches, or whether you'd rather search directly over code in the way that like some other work in the field does. I think that yeah, I think I guess there's pros and cons. Like, I think that if you search over code, it's very unlikely that you get like full photorealism. And so it's going to be very hard to get like high level motor policies working. But at the same time, you like lose some of the semantics that you might have in code. But I guess with the like sort of language steering stuff, you might hope that you get a lot of that back. I would imagine that you would rather do code sort of search type things in like in situations where you actually care about performance in video games, or where you care about like writing good code or doing good math. Like, a lot of these sorts of environments are naturally described in terms of code. And so it might be a better fit for things like Omnific. Or if you want to just do a general agent that's good at a lot of reasoning. I guess like I'm a bit worried about the like gap between like code in the real world and just in terms of the complexity. And it's seemed like all the times we've tried to make games transfer to the real world, it's been very hard.
What are the number of parameters for G2 and G2?
I don't think I can say that, unfortunately.
So it seems like an example of being seeing the locomotion pretty high level and simulating all the environments like move left, move right, move forward, and backwards. Are there any environments that are kind of lower level control? Do you have any ideas like how you can make Genie work those environments?
Well, so at least in Genie 1, the lower level robotics sort of environments, I think that all of the stuff that we're working on is like doesn't overfit to that. Like it's stuff that, like, given changes in the data, I would imagine you could include different sorts of actions that are at a lower level. But yeah, I think it's like a bit of an open question of how would you get an LIDM, for instance, to track the lower order things rather than the higher order things. Yeah, I think that there's like a lot of LIDM research in particular, I think is very like useful for like yeah, like it's a very open space, and I think it's actually easier to do at smaller scales because you don't need to train the whole generative model even in order to evaluate it. The LIDMs tend to be much smaller. And so I would imagine that I guess I'm hoping that a lot of people do like a lot of useful LIDM research that not only gets these sort of low level movement things, but also like can better disentangle different sorts of actions, and can like I don't know, like have like a part of the space which just like I guess disentangle also uncertainty about actions from uncertainty about the environment. Like when I walk into a new room where everything is, like those could be similar features out of an LIDM as we use actions, right?
Okay, is there one more question from the panel speaker again?